going to tell us about the maximal rank conjecture and moduli of curves. Thank you.
All right. So I would like to start by thanking the organizers for my invitation and the chance to be here. And I am going to talk about the moduli space kind of thing. So it's going to be very different from the previous talk. Also, most of the things that I am going to say are pretty old. And they were kind of brought up at the time that I was a graduate student, and there was not much progress for a very long time, so let's see what we can say these days. The setup is going to be with curves. I am interested mostly in curves, and for me, curve C is going to be projective, and I am going to assume that it's defined over the complex numbers, although most of the things that I will say work on any characteristic. But I feel more comfortable over the complex numbers, and not everything works if it's positive characteristic. And then you know that projective curve is one-dimensional thing over C. So from the point of view of real geometry, it's a two-dimensional thing. So it's the Riemann surface. And if it is projective, it is compact, and every compact Riemann surface is a certain number of donuts glued to each other, like this. And the actual number of donuts is called G. So here G would be equal to 3. And that's the kind of thing we want to study. And one of the words that I wrote in here is projective. And what this means is that the curve can be immersed in projective space as the intersection of a certain number of polynomials, a certain number of hypersurfaces. So we are going to think of the curve in projective space. Now, when you think of a curve in projective space, you can think in two different ways. You can think of the object in the kind of where it is, so it is in the space, that's where it lives. Or you can think the other way around. The interesting thing is the C, the curve, and then we have to look at how we put it in there. And when we try to do that, and maybe I should call that R because it's going to be better more compatible with the notation I am going to use in the future. When we are trying to think of the curve is the interesting thing, we try to figure out in how many ways we can put the curve into projective space. And we know that in projective space, we have a nice canonical bundle. And that nice canonical bundle, if we are in PR, have R+1 independent sections. You can pull this back to the curve, and then you get a line bundle on the curve, and you get R+1 sections. So the pullback of PR of 1 is a line bundle. L on C, and it has R+1 independent sections. Now you can go the other way around. If I give you a line bundle and I give you R+1 independent sections, you can put the curve into projective space, and therefore we can go both ways. So the interesting thing here to consider for every curve is the set of line bundles which have this number of sections. And we write GRD of C as the set of linear series of degree D and dimension R on the curve C. And that space is, again, a scheme, and it's well studied, especially when the curve is generic. When the curve is generic, we can say what this looks like. GRD of C is a scheme of dimension number which is going to depend on the genus of the curve, dar, and one more invariant that I probably didn't introduce, which is the degree. The degree is the number of zeros. I should write it here. The d is the number of zeros of a section. If you are trying to think in terms of the projective space that you are looking at, you have the hyperplanes here. In the projective space, they intersect a curve into a finite number of points. You count the points, that's the d. All right, so now let's look at all the set of all the GRDs. Let's assume that C is generic, and then you get a scheme of dimension rho, which is G minus R plus 1, and G minus D plus R. And that means that if this number is less than 0, that the locus is empty. If it is 0, it's a finite number of points. And actually, we can count how many points there are. They have a very natural combinatorial structure, which is the following. If we are saying that this number is 0, what we are saying is that G is R plus 1 times G minus D plus R. And then let's take a rectangle, which is R plus 1 cross G minus D plus R. There are going to be G spots here in that rectangle. We fill these spots with the numbers between 1 and G in all possible ways, so that both the rows and the columns are in increasing order. And the number of different ways of doing that tells you how many different GRDs the curve has. All right, and then if rho is larger than 0, then the locus is connected and irreducible. And in both these cases, we can compute the tangent space through a certain map. Let's assume that the linear series is complete, so there are no more than R plus 1 sections. And then we can identify the GRD with the image in the Jacobian, essentially, because it's going to map in an open set, it's going to map 1 to 1. And then you know that the tangent space to the set of line bundles on the curve is parameterized by the H1 of O, or if you like, the space of sections of the trivial bundle, or if you like, the dual of the space of sections of the canonical. And then there is a natural map, which is called the Petri map, which maps H0CL, and that's the set of space of sections of the line bundle. Then it's a dual, and we just multiply sections, and we land in here. And the tangent space to the GRD at the point CL, assuming it is a complete series, would be the orthogonal to the image of this map. So one way of proving that the GRD is a scheme and it's non-singular most of the time, and of the right dimension, is by showing that this map is injective, because if you look here at the numbers, that has dimension g, the genus of the curve, that we were assuming has dimension r plus 1, and then you use Serre duality and Riemann-Roch, and this tells you that this has dimension g minus d plus r. So we get that when the map is injective, the orthogonal to the image of this map would have dimension g minus whatever you have in here, so that works. Okay, so that's what happens for the generic curve. Of course, if you take special curves, nothing is going to work. And we are going to see in a little while that that's actually an advantage, because we want to study moduli spaces of curves, and we are going to take advantage of the fact that for many curves, these results do not work, and they give us special loci in the moduli space. Now, let's try to study a little bit more the geometry of a projective curve. So far, I mentioned that I have a linear series. Therefore, I know what happens with the hyperplanes that intersect the curve. But in projective space, you have hypersurfaces of other degrees. For example, you have quadrics and cubics and so on. And you want to figure out what these quadrics and cubics and so on cut into one of these curves, and how is this related to the curve itself. And there is a nice conjecture about the behavior of these higher order hypersurfaces, which is the maximal rank conjecture. That was proposed by Harris in the 1980s. And it says the following. Let's assume that you take a generic curve and a generic line bundle on the curve. And I should not say, maybe not a generic line bundle on the curve, but a generic line bundle that gives rise to a map from C to PR of degree B. So essentially, it would be a generic point in this GRD of C. Then we have the H0 of L, which corresponds to the space of sections of hyperplane. If we want to consider quadrics, for example, a quadric is obtained as a polynomial of degree 2 in the linear things in the x0, xr. So what we should do when we are trying to look at the curve is take the symmetric power of the H0 of R. And we can do that for every symmetric power. If we want to look at cubics, we take the third cubic power and so on. So we have this R of the H0 of L. Now that's one space of curves that depends only on the H0 of L and doesn't tell you anything else about the curve. But you can also look at what happens when you multiply the sections and you restrict them to the curve. For example, if your curve is contained in a quadric, and you take here in S2 of H0 of L the equation of the quadric, when you restrict to the curve, you are going to get 0 on the curve, because the curve is contained in the quadric, so it's going to vanish on the curve. So let's consider the map here to H0 of C L to the power R. And the conjecture tells you, pardon? Yeah, I should, let me write K here and K here. Right? I want the same letter here and here, but has nothing to do with the dimension of the R, yes. And what I would like to know is what happens to this map. And the conjecture says that this map should be of maximal rank. So it can be injective when that dimension here is smaller than the dimension there, which will probably mean that K has to be small. And it should be surjective when the dimension over there is smaller than the dimension over here. So the conjecture says that this map has maximal rank. Now, there is a big difference between saying what we are saying for this map and what I was saying over there for the Petri map. For the Petri map, I asked the curve to be generic, but I asked every line bundle on this generic curve to behave well. Here it's very different because I asked the curve to be generic, but I only asked the L to be generic as well. So there can be a line bundle that behaves well and many which don't. So in a way, it seems a much weaker conjecture, and one would hope that would be easy to prove, which has not been the case. That result was proved by Elia and Baliko for k equals 2, and also in some other cases, for example, for non-spatial line bundles and with several additional components. The case k equal 2 has been reproved recently by two groups of people. One is Fu, Osserman, Zhang, and myself, and also using tropical methods by Jensen and Payne. And in both cases, we can say a little bit more than the k equal 2. We can say a few things for k equals 3 and so, but with many additional conditions. And then the result was proved completely for any k by Erik Larsson. So complete proof of the maximal rank conjecture. The initial proofs, as well as Erik Larsson proofs, makes use of the curve immersed in projective space. So it looks at Hilbert schemes and what happens at points of these Hilbert schemes by looking at the generated curves which are singular, and the way they behave. These two proofs over there are a little bit different, and I am going to explain a little bit more later on what the difference is in terms of the maps themselves, because instead of trying to figure out what the kernel of the map is, what we are trying to figure out is what the image of the map is. If there are enough things in the image, then the kernel has to be small, and that's what we would like to see. All right, so what happens now when we don't insist on the line bundle being general? We would like to deal with every line bundle. And I am going to give you some results that work for very small r, and then see what we can expect if we want to get larger values of the degree. So let me prove you the following, or give you a sketch of proof of the following result. If C is a general curve, and L is a line bundle, of degree at most G plus 1, then the map from the second symmetric power of the line bundle to H0 of L square is injective. So again, here the curve is general, but the line bundle is anything. Now, the method of proof is very similar to the method in which that was used to prove, for example, the Petri conjecture. What we need to do is prove something for a general curve. That condition that we are writing here is an open condition because we are asking a map between vector spaces to have the largest possible rank. And you know that when you teach linear algebra, that when you want to see that a map of linear spaces does not have maximal rank, you have to write certain minors equal to 0. And these are equations, therefore, the locus where this fails should be a closed set. So if we can find a curve for which the condition is satisfied, then it's going to be true in a neighborhood of that curve. Then what we need to do is we need to choose the curve the right way. We want to do that for a non-singular curve, but non-singular curves are very difficult to treat. So what we do is we take a curve which is singular, but still behaves in the best possible way. The traditional curve that was used at the beginning for this kind of results of perimeter theory that I wrote over there were curves which had some elliptic tails, but somebody figured out, actually Welters figured out, that there are curves that behave much better than those, which are chains of elliptic curves like this. These are very well behaved, and they are much easier to deal with than anything else. So let's try to degenerate to a curve like that. And now let's try to prove that we take any line bundle on that curve, take the space of sections, then this map has to be injective. And the way we can do that is try to see what happens. Essentially, what we want to do is not any line bundle on that curve, because that's going to be false, because this curve has line bundles of degree g+1, which are very, very bad, because they have very negative degrees in all these components and very positive degree over here, and then that space of sections is going to be far too big for the map to be injective. But the things we care about are not what happens on the curve itself, but what happens that could come as a limit of something you have in a curve nearby, which is non-singular. So we need to figure out what happens to a linear series on a curve like this one when it comes close to the curve we have over there. And if we have a family, say parameterized by a curve, that thing here is going to be a divisor, so it corresponds itself to a line bundle. And actually, every one of these components, if the curve is nice, it's going to be a divisor, so it corresponds to a line bundle. Which means that if we have a line bundle on the family, which is a limit of line bundles on the various curves over here, we don't have a unique line bundle on this curve, because we can modify it any way we want by adding multiples of the components that are on the special fiber. We won't change anything on the generic curve. We are going to change things only on that special curve. That seems like a disadvantage, but again, it's an advantage, because it means that we have many different line bundles that we can look at. We can choose our line bundle so that all of the sections that we would have on the generic curve come to that curve, and we can do it so that they come maybe to sections to just one component. If we make sure that all the degrees here and the degree on the other components doesn't matter, then we are going to get all the sections on one component. And we can do it in different ways, so we can compare what happens when we look at what happens on the first component, or when all the sections are on the second component, and so on. So we do it, and we compare what happens, and we get with a collection of maps like this, and now we have to see what we can say about these maps. And the first thing that we can say is, if we have an element in the kernel, and we look at the version of this element when we bring all the degree on the first component, then it's going to vanish at any point, but for example, at the first point with multiplicity at least 2. So maybe I should label this point. Let me call this point P1, and then point here is going to be Q1, and I am gluing Q1 to P2, and so on. And over here, I am going to have QG. So I have 2 interesting points on every component, which are the points at which we glue. And on the first and last component, I arbitrarily choose one first point and one last point so that it all looks the same. All right, so this section vanishes with multiplicity 2 at P1. And then I compare what happens with that version of the section with the version that is good for the second component. And I see that every time that I move one, the order of vanishing has to increase in 2 units. And then when I get to the end, I would have order of vanishing at least 2 plus 2g. And I was assuming that my line bundle had degree at most g plus 1, so anything of degree less than g plus 1, it's not going to be good. And for degree g plus 1, I have to look a little bit more carefully, and it doesn't work either. So that is the end of the proof, and I am done. Now let's look at how good that bound is. And what I claim is that this bound is as good as it can be. As soon as I take the degree to be at least g plus 2, any curve, I can find line bundles for which the map is no longer injective. So see generic curve. There exists an L such that the map is no longer injective. And I'm going to show you how I produce that L and how I get the map. What I do first is look at line bundles. I am going to consider only the case of G even. I actually do not know what happens for G odd of exactly that degree. So G even, and I am going to look at line bundles of degree, I think it's G plus 1 over 2. So let me look at the G plus 1 over 2, 1. And then you compute the real net number. Yes? I want G even. Let me see. All right, you're right, because I want G plus 2 over 2. Thank you. All right. Yes?
I don't understand how that proves that the statement holds for every line on the generic curve. So why couldn't, so the generation argument you have
Right.
seems to work for the generic line bundle on the curve, not for every line bundle.
No, it's the same kind of argument that you would do for you degenerate the curve, but
Yeah, okay,
every line bundle.
That's okay, but then you might have on some curves some line bundles for which the map is not injective. Does that exclude that?
No.
Okay, we'll talk about it.
We'll talk about this later, right? But it's the same, if you believe the argument for the Petri map, and I am sure that you do believe it, it's the same exact argument, because for the Petri map, you show that for every line bundle, and you degenerate the curve, right? Because the Picard variety is the limit of the different Picard varieties. And if you prove it for every line bundle on the special curve, then it's for every line bundle on the generic curve.
All right.
Okay? All right. So let me continue with that. I have a generic curve and of even genus, so that this is an integer. Thank you. And now, if you compute the number over there, you are going to find that this is non-empty, and that's finite. Finite, and finite is not just one point, but it has plenty of things, like the many different ways in which you can fill these boxes. So I take two different ones, L1 and L2, different, in G1, G plus 2 over 2. And then I take L to be L1 tensor L2. And my claim is that L has 4 different sections. It's not hard to prove that it has exactly 4 sections, but there are 4 sections which are pretty obvious. I have L1 and L2. Both of them are here, so both have 2 sections. Let me call the sections S1 and T1 the sections of L1, and S2 and T2 the sections of L2. So from here, L is the product of these two. So if I multiply a section of L1 with a section of L2, I am going to get a section of L. And I can do this in 4 different ways. I can do it as S1, S2. I can do it as S1, T2, as T1, S2, and T1, T2. Now what I want is something in S2 of H0 of L. So I have to take symmetric powers of these things, which I can do easily. For example, I can take S1, S2 tensor T1, T2. That's not symmetric, but if I take this plus T1, T2 tensor S1, S2, that's in S2 of H0 of L. And I could also take S1, T2 tensor S2, T1, no, T1, S2 plus T1, S2 tensor S1, T2. That's also here. Now, when I map these 2 sections to H0 of L square, both of them are going to map to S1, S2, T1, T2, twice that, right? So if I take the difference of these 2 sections, I get an element in the kernel. Okay. All right. Now, the fact that when the degree increases, the map is not injective, it's not surprising, because if you look at how the right-hand side grows, that's going to grow linearly in the degree, while the left-hand side is going to grow quadratically on the degree, if the K is 2. So you would expect that at some point, things stop being injective and start being surjective. I don't think that this is either of the two. As soon as the genus is sufficiently large, it's certainly not injective. I show you an element in the kernel, and it's not surjective either if the genus is sufficiently large. All right, so what is the right conjecture if we want to deal with every line bundle? And Farkas came out with a kind of improvement of the maximal rank conjecture, which is the strong maximal rank conjecture. And actually, it's only for k equals 2, at least as far as I know. So that's in a paper by Farkas and Aprodul. And what they propose is the following. Let's look at the map from S2 of H0 of L to H0 of L square as kind of a map of vector bundles living on the GRD of a curve. What we said is that this GRD of the curve has dimension rho that we compute over there. And that's a map of vector bundles over here. We can make that things continuous on the L. So what we would expect is that if we impose that this map doesn't have maximal rank, the number of conditions would come from the number of conditions that you need to write down when you write that a map is not of maximal rank in linear algebra class. You look for a determinant which is different from 0, of dimension 1 less than the maximum, and then you write all the minors that you can obtain from this smaller determinant by adding 1 row and column and see how many conditions that gives you. So you would expect that the dimension of the locus where this map has not maximal rank is the dimension of the base, which is rho, and then minus, let's see how many conditions we need to write here. We said that the H0 of L has dimension R plus 1 because it corresponds to projective dimension R is 1 more in terms of the dimension, so R plus 1. All right, so the S2 would have dimension R plus 2 choose 2. And the H0 of L square, if L is a little bit big, it's going to behave well in terms of Riemann rock. We don't need to worry about the H1. So that's going to have dimension most of the time 2D plus 1 minus G. Then the number of conditions we need to write down is, let's assume that that's smaller than the other one. It doesn't matter, actually. We have our matrix here. We have chosen, so here we have the R plus 2 choose 2. We leave one space here, and here we'll have also the R plus 2 choose 2 minus 1, and then the difference here is the number of conditions we need to write. So that's going to be 2D plus 1 minus G minus R plus 2 choose 2 minus 1. The strong maximal rank conjecture would say that if the curve is generic, that the set of line bundles where the condition fails has this dimension. That's the conjecture. For example, if you go back to the example I gave you here of the case of even genus 2 and degree G plus 2, and you compute the numbers, you get something, you expect something 0-dimensional. And what we found was 0-dimensional because the way we found it was taking pairs in a 0-dimensional set and combining them. So far, so good. I do not know if these are the only ones, and I do not know if these are all the ones. So that's for future research. Now, that's maybe entertaining, but it's probably not that useful. But there are other uses of this maximal rank conjecture, which were also suggested by Farkas. That seemed a lot more interesting. And they apply to understanding moduli spaces of curves. If you look not at one curve at a time, which is what I have been doing so far, but instead want to look at all the curves of a fixed genus, you get something really nice, what's called the moduli space of curves of genus G, which is written MG. Now, this MG is very nice, but it's not projective. If it has some singularities, but they are not too bad. But there are plenty of curves, like the example over there. You have non-singular curves, and you let them degenerate, and they are singular. If we want to have something projective, you need to compactify it. And it turns out that there are very different ways of compactifying, many of which are very interesting. And there is a whole program by Hassett and Gill and many other people who have studied the various compactifications. But I am going to go with the classical one, which is the simplest. You just take the non-singular curves and you add nodal curves. So curves which have only nodes as singularities. And that compactification is called mg bar. So these are nodal stable curves. And stable means just not too many automorphisms. For example, you don't take a non-singular curve and you add a rational curve to it glued at a point, because when you do that, you know that the P1 has lots of automorphisms. If you just fix a point, there are still plenty of automorphisms left. That would make your moduli space to be not very nice. So you need to make sure that there are not too many automorphisms. But that's not that hard. All right, so now let's try to study this mg bar. And that's not a new problem. Classical geometers were studying these mg bars, or maybe without the bar, just the mg's. And they came out to the conclusion that they were probably all rational, because they were starting with the beginning. And if you look at genus 0, there is not much to study. There is only one rational curve. If you go to genus 1, you probably heard that the plane cubics are the rational curves, and the plane cubics, you can write their equations. You can write the curve of genus 1 as y squared equals x minus 1, x minus t. And essentially, that t tells you what the curve is. So depending on one parameter, it should be a line of elliptic curves. If you go to genus 2, it's a little bit more complicated, but every curve of genus 2 is a double cover of the line. You have to look at how many ramification points there are, and the ramification points tell you what the curve is. So again, they are parameterized by just, I think it's 6 points up to the automorphisms in P1, so that gives you 3 parameters and classifies the set of curves. And you can go on. Genus 3, you have plane quartics, so the coefficients of the plane quartic will give you parameters and so on. But things become more complicated, and not all these moduli space are rational or even unirational. It was thought that they were, and I think up to genus 13, all these moduli spaces are unirational. Unirational means there is a projective space that maps onto an open set of the moduli space. All right, so what should we do after genus 13? And it actually came as a surprise that they are, when genus is at least 24, they are as far away from being rational as they can possibly be. The question is, how do you measure how rational something is? It's rational or it's not rational, right? But what is there in the extremes? And that is measured by why it's called the kind of varieties of general type. So what you can do when you have x of dimension n, which is either non-singular or with mild singularities so that everything can be defined nicely. You take the tangent space, you take its dual, and you take the highest power of its dual, and that's the canonical bundle. And the question is, if you take sufficiently high multiples of the canonical bundle and you use them to map X to whatever projective space you are able to map it, what's the dimension of the image? And the dimension of the image, first, it's possible that you have no sections at all for any multiple of the canonical. That happens for the projective space because the canonical is negative. And so if multiples of the canonical have no zeros, then the Kodaira dimension of X is, by definition, negative infinity. But if they have zeros, then you look at how big the image can be of X. So you map X. So otherwise, map X by MKX and look at the largest possible dimension. Of the image. And that's the Kodaira dimension. And the variety is of general type when the Kodaira dimension equals the dimension of X. And that happens actually for moduli spaces of curves of genus at least 24. That's a result of Harris, Mumford, and also Eisenbach. If G is greater or equal than 24, then mg bar is of Kodaira dimension. The dimension of mg bar, which is 3g minus 3. So it's a variety of general type. The way they proved that result was by trying to figure out how you can write kind of an ample divisor on mg bar. They need to figure out first what is the canonical class, and they did that. They computed the canonical class of mg bar. If I recall that correctly, well, first, how do we write that? The Picard variety of mg bar is known, and there is something coming from the interior from mg. The class is called lambda. So that should be a bar as well. So that's spun by lambda, which is coming from the Hodge bundle. And then the classes on the boundary. We said that mg bar is obtained from mg by adding nodal curves. We have to look at what kind of nodal curves we can get. We can get an irreducible curve where we just identify 2 points that gives you something which has codimension 1 in mg bar. It's called delta 0. It's the class of curves like this. And then we can make reducible curves as well by taking components, one of genus I and the other of genus G minus I. And that I could move between 1 and up to G over 2, right? The number, the closest number to G over 2. And then they compute the KMG bar, and that turns out to be 13 lambda minus, I think it's 2 delta 0, minus 3 delta 1, minus 2 delta 2, up to minus 2 delta G over 2. Then one has to figure out what's the ample con, and that was known as well. And the trick now is try to write a multiple of the canonical and showing that this is ample. And you can reduce the problem to trying to find a divisor in MG which has the suitable expression in terms of the lambda delta 0, delta 1, and so on. So they saw that what they needed to find was a divisor which is effective that divisor which is effective, we can write this as A lambda minus B 0 delta 0 minus B1 delta 1 up to minus B G over 2 delta G over 2. And you need to have the coefficients to satisfy some relations. And I think the relations you need are that something like that A over B, let me see, I have them written here, has to be at least at most 13 over 2. So you need A over BI to be less than 13 over 2, and A over B1 to be less than 13 over 3. And that is enough to show general type. So the question is, how do we find these divisors? And it has to be effective. Now, MG bar, the way to describe divisor is try to find a set of curves, right? A divisor is a codimension one set of curves which has some description. And the description that was used originally was in terms of the Brill-Netter theory that I explained at the beginning. I said that for a generic curve, the dimension of the space of linear series is G minus R plus 1 times G minus D plus R. And there aren't any if the number is negative. Now, the negative numbers, you would expect that the more negative it is, the fewer curves there are. And in particular, when the number is negative 1, you expect a divisor in MG bar. And actually, that's known to be the case. When the number is negative 1, it's a divisor. When the number is smaller than negative 1, then there might be things that don't go as planned. But for negative 1, everything works. There is a divisor. And then you have to choose the divisor. And the difficulty here is we want the divisor to have a class that satisfies this condition. The divisor that was used, the first one that was used, was the case in which you take R equals 1. And then you need G plus 1 is supposed to be R plus 1, G minus D plus R. So when G plus 1 is even, so when G is odd, there is a divisor that you can compute. The G you have fixed, right? The R we set is 1, so that allows you to figure out what the D should be. There is a choice of a D, only one, that gives you the right divisor. That divisor exists for every genus, greater than 24 or smaller than 24, so long as it is odd. Now, the problem is that when the genus is small, these conditions are not satisfied for the expression of the class of the divisor. So that wouldn't prove you that the moduli space has general rank. And for even genus, you have to take different divisors. They can come, for example, from studying the Petri map. But for genus 23, 22, and so on, that doesn't work. And what Farkas proposed was to look at the set of line bundles for which, or so the set of curves for which the dimension of the locus of the map is not, the maximal rank conjecture is not satisfied for particular choices of the D and the R. And for genus 23 and 22, there are some good choices. So for genus 22, you should look at G625 when S2 of H0 of L to H0 of L square has dimension, so the locus where this fails. If you compute the numbers, you expect to have a divisor in MG. And for G equals 23, you have G626, I think you need. And the locus also is supposed to be a divisor. One can compute the classes of these divisors, and these classes would help you in terms of showing that the moduli space has maximal codirected dimension. The main problem here is the maximal rank conjecture has been proved, but only has been proved for generic curve and generic line bundle. If we want to make sure that we get a divisor that way, that's not enough. We need to prove that for generic curve and any line bundle, that maximal rank conjecture is satisfied, right? And that's one of the hard parts. Now, that hard part for these particular values of genus and degrees and ranks is done. So we do know that in these two particular cases, the strong maximal rank conjecture holds. And that has been shown again independently by the same two group of people that I mentioned before. So on one hand, Fu Osserman, myself and Zhang, and Jensen and Payne. That method uses tropical geometry. That method uses change of elliptic curves, but actually the tropical curves that are used by Jensen and Payne and the kind of change of elliptic curves behave exactly the same way in terms of linear series. And again, we need to show that the map is not that it has no kernel, but that there are enough sections which are linearly independent in the end. And it requires a lot of study and a lot more careful analysis than in the prior cases. Now, there is a little thing that this is not yet sufficient to conclude that for genus 22 and 23, to have maximal codirected dimension, we need to also show that there is no ramification when you go down from the G's to the M's. So if you think of the G as located above the moduli space, it might be that you go down to the M's and you lose components. So you have a nice component with the nice class over there, but you map it down and something maps to codimension 2, and then it would not give you the right divisor in MG. So that still needs to be checked. And I am going to leave it here. I think a lot of things, for example, the proof by Jensen and Payne, I think works in an arbitrary characteristic, but the previous part of Farkas about applications to moduli space are done for characteristic 0. So there is a lot of things to be done Yeah, you can probably ask the same questions, but don't ask me to answer them, please. Yeah, some things can be done, but there are things which have been done only in characteristic 0, and I don't know if there are ways around to apply them in any case. The last piece is missing still, so it's not yet known.
Okay. So, but can you repeat? So the point is that when you look at GRD's G625 over MG, over M22, then you have a problem with the map 2MG.
Right, the computation of the class is up there, not down there, so one should see what happens. The computation of the class was done before it was known that it would behave well, right? So that the generic curve did satisfy the maximal rank, the strong maximal rank conjecture. And that little piece of the mapping is still not solved. It's hopefully doable, but we'll see. There is still a gap. There is still a gap. So I think from 14 up to 21, it's still open.
Techniques.
Well, the problem is that all these divisors, you can define them. But when you compute the numbers, they don't help you in proving. So you need this condition on the coefficients of the divisors. And these are satisfied for for genus sufficiently large, but they no longer hold. So you probably need to come up with other divisors that would satisfy the condition. Or maybe they are not of maximal codired dimension. It may be, I mean, I don't know if they are closer to 24 or they are closer to the ones that are known to be unirational, right? So maybe some are unirational, maybe, I don't know where the divide is. Where it breaks, well, I hope that 22 and 23 are maximal codired dimension because there is so much evidence by now. I might be wrong. I have no idea where in the middle things break. I don't think so.
No other question? Well, thank you.